hyperspace were real, what terrifying dangers might be hiding in the great unseen? And could it ever be more than just a sci-fi fantasy? From wormholes to warp drives to hyperspace lanes, science fiction has handed us wildly imaginative ways to cheat the cosmos. But is any of it actually possible? And what even is hyperspace? Let's dive headfirst into one of the most mind-bending concepts in all of science. Hyperspace is a fascinating idea that bridges the gap between hard science and pure imagination, often serving as a stand-in for faster-than-light travel in speculative stories. Its portrayal varies dramatically, showing up in massive science fiction franchises like Star Wars, Isaac Asimov's Foundation series, and television shows such as Babylon 5. At its core, hyperspace refers to an alternate dimension or higher dimensional space that lets travelers completely bypass the normal constraints of our universe. Instead of being shackled by the cosmic speed limit, the speed of light, hyperspace offers a theoretical shortcut, enabling breathtaking journeys between impossibly distant points of the cosmos. While the term hyperspace doesn't have a direct or universal counterpart in current scientific models, it draws heavy inspiration from real physics concepts, such as higher dimensions in string theory, wormholes, or the manipulation of space-time itself. Its interpretation in science fiction reflects as much raw narrative creativity as genuine scientific plausibility. In science fiction, hyperspace isn't just a tool for traveling faster than light. It's a powerful narrative device that shapes entire worlds and the stories built around them. In Star Wars, hyperspace lanes offer established routes for interstellar travel, creating bottlenecks for trade, piracy, and devastating battle. In Dune, the Spacing Guild's folding space ability allows instantaneous movement through a mysterious, navigationally treacherous dimension. Meanwhile, Babylon 5 envisions hyperspace as a genuinely dangerous alternate realm where navigational beacons are absolutely essential to avoid getting hopelessly lost, and ancient ruins drift through its void, waiting to be stumbled upon by unwary or adventurous travelers. Ironically, Hyperspace from Isaac Asimov's Foundation, widely regarded as the greatest sci-fi book series of all time, is probably the least thrilling version. You engage the engine after performing incredibly complex calculations, vanish, and instantly re-emerge, hopefully at the right destination. But there's no passage of time and zero explanation for how the system actually works. That approach is honestly brilliant for sci-fi storytelling. Don't waste precious time trying to explain a fantastical system whose only real purpose is to solve the enormous problem of crossing the staggering immensity of space on human timescales. This method avoids unnecessary exposition and the very real risk of embarrassing math or physics blunders. However, it also sacrifices the chance to embrace the deep intrigue that a mysterious shadow reality could bring to a story. To strike a balance, this exploration will delve into how hyperspace is depicted in some of the more richly detailed works of fiction, providing inspiration for anyone crafting stories set in strange, non-Euclidean realms or dimensions existing at right angles to our own reality. Of course, the main focus will be on discovering whether hyperspace holds any genuine potential as a method for traversing the galaxy without taking the impossibly long scenic route, or if it truly is nothing more than science fiction. The idea of venturing into a dimension beyond our comprehension strikes at something primal, our deepest curiosity and unstoppable thirst for exploration. Hyperspace also comes with its own set of fictional rules, navigation challenges, unique physics, and even strange entities, making it just as fascinating as the ships or people that use it. Drifting helplessly off a beacon into uncharted hyperspace and encountering spacecraft living there, or stumbling upon ancient abandoned stations and relics left in deep hyperspace, these make for absolutely thrilling tales. But its key appeal lies in offering a solution to the staggering vastness of space, while raising profound questions about what lies beyond our understanding. Remarkably, many depictions of hyperspace accomplish this without outright violating Einstein's theory of special relativity. The earliest science fiction reference to hyperspace for travel appears in Hugo Gernsback's Amazing Stories around 1931. However, the term itself predates modern sci-fi, tracing back to the 19th century, where it was used to describe higher dimensional spaces. This was before Einstein developed his theories of relativity, during a period when even some serious scientists speculated that stage magician tricks or complex knots might be exploiting four-dimensional space to function. But they weren't thinking about it for space travel. In the early 20th century, science fiction didn't grapple much with the true mind-bending scale of the universe. The term galaxy is ancient, dating back to Greek civilization, and first appeared in English in Chaucer's works, describing that big, dense band of stars in the sky, the galactic disk. Over time, humanity began realizing we were actually inside that disk. However, it wasn't until Edwin Hubble's groundbreaking work in the 1920s that humanity realized galaxies were distinct islands in a vastly wider universe, and not particularly spherical islands either. Before that, the universe was often assumed to be infinite in size, eternal in age, and relatively homogeneous in distribution. As theories of special and general relativity became more widely known, and the true scale of the galaxy was better understood, science fiction began to reckon with the monumental challenge of interstellar travel. Writers introduced various mechanisms to explain faster than light travel, from warp-style drives, like those in Star Trek, which allow superluminal movement within normal space, to devices that take you instantly to another location by folding space itself, and those that involve jumping into an alternate dimension, traversing it, and emerging back into normal space at a congruent point. Now, there's no need to spend too much time explaining why we can't travel faster than light under normal circumstances. This has been covered in detail before, but a quick overview is absolutely appropriate here. The term light speed is not the most accurate name for this universal limit. Light, along with other massless particles, travels at this speed precisely because they lack mass. Nothing with mass can ever reach or exceed it. We first measured the speed using light, so the term stuck, but a far more accurate description would be the speed of causality, as it represents the maximum rate at which useful information and cause and effect can propagate through space-time. Thinking of it this way makes it intuitively clear why exceeding the speed of light would inherently imply the ability to travel backward in time and alter the past. Things with mass experience time. Massless particles like photons do not. When an object with mass accelerates, more of its total energy shifts from resting mass energy, described by the famous equation E equals mc squared, into other forms like kinetic energy. You've almost certainly heard that as you speed up, your mass appears to increase, meaning every additional boost in speed demands even more energy to push further. This escalation grows exponentially, ultimately requiring infinite energy to ever reach the speed of light. Modern physics actually avoids distinguishing between rest mass and relativistic mass because it's far more accurate to think of that added mass as kinetic energy. Energy in every form warps space-time and demands effort to accelerate or manipulate, whether that energy takes the shape of mass, kinetic motion, heat, or rotation. Consider this. A spinning or heated object actually requires more force to accelerate than its cooler, non-spinning counterpart. Here's the mind-blowing part. At everyday speeds and conditions on Earth, nearly all the energy locked inside objects exists purely as mass energy. A simple glass of water contains a staggering amount of mass energy, far more than what's unleashed in a typical atomic bomb, while only a minuscule fraction of its energy comes from thermal, kinetic, or gravitational potential sources. This is exactly why we, along with that humble glass of water, experience time at nearly its maximum rate. Virtually all our energy is bound up in mass, and that mass portion is what experiences time. As an object speeds up, heats up, or spins faster, the proportion of its energy coming from mass shrinks. Same mass, but dramatically more total energy. And as a direct consequence, it experiences time more slowly. For instance, if half an object's energy is mass energy, it will experience time at half the normal rate. But here's the crucial catch. No matter how fast you accelerate, heat, or spin an object, some portion of its energy will always remain tied to mass, meaning it will always experience time, just at an increasingly slower rate. Complete time dilation, the kind that photons and gravitons experience, remains forever out of reach for anything possessing mass. The reverse is also true. Even a low-mass cold object drifting far from any galaxy's gravitational pull still carries some non-mass energy and therefore experiences some degree of time dilation. To even contemplate traveling beyond the speed of light, we need to wrestle with concepts like imaginary mass, similar to imaginary numbers such as the square root of -1. Importantly, this is imaginary mass, not negative mass. Negative mass plays its own theoretical role in bypassing light speed, but in a completely different context, often involving wormholes or warp drive travel. However, neither negative mass nor imaginary mass is inherently required for hyperspace concepts. Hyperspace as a fictional construct appears in countless forms, yet in mathematics it's actually an older term describing higher dimensional spaces, where structures like tesseracts can theoretically exist. A tesseract is the four-dimensional equivalent of a cube, just as a cube is a three-dimensional version of a square, which is a two-dimensional version of a line, which itself is a one-dimensional version of a point. The most common interpretation in science fiction portrays hyperspace as a distinct realm of space connected to our universe, where travel is dramatically faster or distances are effectively compressed. But sometimes hyperspace is imagined as an entirely separate universe with subtly different properties, like a faster speed of light, or being smaller or younger compared to our own universe's vast size and ancient age. For instance, imagine you could tether yourself to a specific position in our universe, then leap back to an earlier period where everything was closer together due to Hubble expansion, the stretching of space itself. You could theoretically travel to another location near the speed of light, then return to the present and emerge incredibly far away. This works because in the earlier universe, those 2 points were much closer, and over time, Hubble expansion spread them dramatically apart. Notably, Hubble expansion allows distances to increase faster than the speed of light, since it is space itself that's expanding, not objects or information moving through it. However, this method inherently permits time travel, which completely shatters causality, the very fabric of cause and effect. To sidestep such dangerous issues, hyperspace must instead involve traveling to a parallel universe that is congruent to our own, a universe where conditions align with ours in certain critical ways. But what exactly is a congruent universe? In geometry, two shapes are congruent if they are the same size and shape, even if they are rotated, flipped, or moved. For example, two triangles are congruent if all their angles and side lengths are perfectly equal. A map ideally is supposed to be congruent to the place it represents, though flat maps and spherical planets make that remarkably tricky. So generally, congruency means in agreement or in harmony, and in physics it describes systems that share similar properties or alignments. There's no official concept in physics for a congruent universe, but generally a congruent universe is a hypothetical parallel universe that shares a staggering degree of similarity with our own. It might have identical physical laws, spatial structures, and cosmological properties, but with slight variations that make it unmistakably distinct. In this context, a congruent universe would be one that matches our own at a specific moment in time, like an overlay of our universe's past or future state, but without the devastating causal paradoxes introduced by direct time travel. This congruence implies a powerful connection that allows you to map locations in one universe onto corresponding locations in the other, and vice versa. Imagine if you could step onto a physical map of your state or country, walk a few inches to another spot on the map, and then emerge at the corresponding location in the real world. However, your travel would be strictly restricted to those mapped points. You couldn't step from Los Angeles to Tokyo on the map and magically reappear in New York instead. This map ensures consistency and prevents arbitrary jumps, maintaining a rigid, logical framework for travel. Faster-than-light travel would completely revolutionize our place in the universe. But are there ultimate scientific limits, barriers like FTL and hyperspace, that even the most brilliant minds cannot overcome? Could we one day reach a point where we understand absolutely everything, where no mysteries remain? Or will breathtaking new frontiers always await just beyond the next horizon? These are some of the most profound questions humanity has ever dared to ask. With that extraordinary thought in mind, Let's continue exploring what these mind-bending possibilities could truly mean for the future of civilization. With that context in mind, let's warp back into the mysteries of hyperspace. Folding space generally assumes a different approach. Imagine folding a two-dimensional map so that 2 points touch. In this case, the fold occurs through a higher dimension, our three-dimensional universe. Fold space drive extends this concept, folding three-dimensional space through an even higher dimension, or hyperspace, so that two distant points touch. However, how you actually jump between those points on the folded map is often terrifyingly unclear. Same for where you're getting the energy to fold that map, which is absolutely not going to be free. Additionally, if those 2 points actually merged or got stuck together, devastating issues could arise, such as gravitational interactions pulling nearby stars or objects together, potentially triggering catastrophic events like collisions or massive explosions. So you probably only want a temporary overlap and fold. Maybe space-time would resist being folded, and it takes enormous energy to fold and press spaces together before they spring back to an unfolded state. In scenarios involving congruent spaces, the assumption shifts dramatically. Neither the space involved is hyperspace itself. Instead, both exist within a broader hyperspace. Think of it like a pair of maps in an atlas, where the atlas itself is a three-dimensional book or part of a library filled with maps of varying sizes and scales. In this type of hyperspace, a congruent universe might be one where distances between points are compressed, or the topology is altered in a way that makes travel faster or more direct, or the speed of light or causality is simply higher. That probably would have real consequences on objects that made the jump too, as it might imply entirely different behavior of mass, which could be a serious problem since your spaceship and everyone aboard is made from it. In this case, you wouldn't be time traveling. Instead, you'd be navigating through a snapshot of a universe with altered spatial properties, but still aligned with our own in essential ways. This alignment or congruence ensures you could safely re-enter our universe at a corresponding location without creating paradoxes or disrupting the natural order of either space. There are also cosmological models in which this might actually be viable. If string theory turns out to be correct, then you not only have extra dimensions with many universes both like and unlike our own within them, including different particles and physical constants, but also interactions between those spaces. Indeed, it is assumed that a collision or intersection of various branes can cause a Big Bang event, and something on a smaller scale should be possible too, as might practical travel between them. And since they do occupy locations in a wider hyperspace, mind-bending shortcuts might genuinely be possible. It's also worth noting at this point that brane cosmology theory allows for a sort of higher dimensional area between universes, often called the bulk, which is an actual mathematical hyperspace. It is to regular space as a hypercube is to a cube to a square, or a sphere to a circle. There has been some speculation about using this for faster than light travel, but of course it's wildly conceptual at this point, as is everything else involving hyperspace. If true though, this could unlock travel not only to other parts of our universe's brane, but to entirely different universes as well. It's one possible framework for how all sorts of portals and other intra-universal higher dimensional shenanigans might actually be explained. Think of our universe as a piece of paper, which is basically two-dimensional, but has a tiny three-dimensional component. When we talk about extra dimensions that are compactified or too small for us to see, for string theory or M theory, that's the core idea, that we are a three-dimensional sheet of paper in a four-dimensional universe. Or even a five-dimensional version of a string, itself basically one-dimensional, but having a small component of two other dimensions, not just one smaller hidden dimension, or sometimes 10, 11, or even 26 total dimensions. As a chilling aside, it's also worth noting that any spaceship traveling through higher dimensional hyperspace might be violently torn to shreds. This is due to the distribution of forces over distance squared versus cubed. Forces like gravity or the strong nuclear force are predicted to dissipate far more rapidly the more dimensions you add. So dramatically, in fact, that all molecules may simply fail to hold together in a four-dimensional space, like the bulk. You would dissolve into elemental particles. This would require travelers to be contained within some sort of bubble or tube of flat three-dimensional space as it made its voyage, which we might call a subspace. Conceptually, imagine you are a stick figure drawn on a piece of paper. You cannot survive without being on a piece of paper. You must be drawn on something. So if you want to fly to the other side of an office, someone must fold the piece of paper you're on into a paper airplane and hurl you there. That paper airplane is the safe three-dimensional bubble, and the office is the bulk interpretation of hyperspace. This concept originates from string theory and M theory, where brain literally comes from the word membrane. This and other concepts of hyperspace allow for speculative faster-than-light travel, while avoiding the pitfalls of altering history or violating causality, a recurring nightmare in many faster-than-light theories. It also opens absolutely fascinating possibilities for how alternate dimensions or realities could intersect with our own, providing a fresh framework for both storytelling and theoretical exploration. But both versions, folding normal space through hyperspace or traveling between two parallel universes existing in a wider hyperspace, are fundamentally different from notions of jumping into hyperspace and traveling within it, like we see in Babylon 5. This is probably the most fleshed out example of this style of hyperspace in a major science fiction franchise, so let's delve into it. In Babylon 5, hyperspace is depicted as a separate dimension that allows for faster-than-light travel. Travel to and from various parts of the galaxy is done by first entering hyperspace, then leaving at precisely the right place. Hyperspace is accessed through jump points, created by powerful devices known as jump engines. These engines tear open a rift between normal space, known as real space, and hyperspace. Larger vessels like warships or capital ships come equipped with built-in jump engines, which is incredibly useful for avoiding the impossible military bottlenecks that jump gates would create. Meanwhile, smaller ships or older civilian craft depend on pre-existing jump gates scattered across the galaxy, all remnants left behind by ancient and mysterious races who don't seem to be around anymore. Hyperspace is a chaotic and wildly unstable dimension filled with swirling energy fields that make navigation extraordinarily challenging. Ships rely on beacons, navigation points that provide fixed coordinates to plot their courses through hyperspace. Without these beacons, navigation becomes virtually impossible, and ships risk becoming lost forever in the void. Advanced civilizations like the Minbari can navigate hyperspace far more efficiently thanks to their superior technology. And the even more ancient and powerful Vorlons are secretly the original architects behind the entire system. When another species of equal age appears, their method of entering and exiting hyperspace looks dramatically different from what every other race uses, all of which is based on that original Vorlon design. It's also strongly implied that hyperspace extends beyond our own local galaxy, but not reliably, making intergalactic travel completely impractical. Something strikingly similar exists with the warp travel used in Warhammer 40,000, which is also limited to in-galaxy travel only. And in that case, the hyperspace, or warp, is more or less literally hell, which is also the terrifying premise behind the film Event Horizon. In both Babylon 5 and Warhammer 40K, hyperspace is absolutely not a safe or benign environment. Ships without proper navigation or shielding can become hopelessly lost or utterly destroyed. In Warhammer 40K, the primary beacon sits on Earth and is fueled by potent telepaths, which makes perfect sense since the warp is a psychic realm, similar to the astral plane often used for travel in fantasy series, a realm of pure mind. But in Babylon 5, telepaths also exist, and they do possess a stronger ability within hyperspace, though the reason why is never fully explained. Abandoned or derelict ships and ancient structures are known to drift endlessly through hyperspace, creating an overwhelming sense of foreboding and danger for travelers. This shows up in both the spin-off series Crusade and the TV movie Third Space, where a mysterious relic is found floating in hyperspace that turns out to be a gateway to yet another realm beyond both normal space and hyperspace, one absolutely teeming with murderous, telepathic, and xenocidal aliens. What's truly fascinating is just how many parallels Babylon 5 and Warhammer 40K share in their hyperspace setups. Both feature the concept of a treacherous alternate dimension used for faster-than-light travel, absolutely rife with dangers and navigational challenges. Warhammer 40K also shares the idea of navigators with the Dune franchise, mutants who can chart a path through the twisted reality of faster-than-light travel, though calling it sharing might be generous since Warhammer 40K clearly borrows heavily from Dune. In Babylon 5, there's a later discovery that organisms are actually native to hyperspace, or at least assumed to be, which adds even more mystery and danger to this terrifying alternate realm. Meanwhile, Dune's navigators aren't exactly navigating in the traditional sense. As best as anyone can tell, the calculations required for hyperspace travel are nearly impossible, and their society has completely banned the computers capable of performing them. Instead, navigators rely on limited precognitive abilities to glimpse potential futures and presumably choose the one where slamming the jump button doesn't end in their spectacular fiery destruction. In some settings, there isn't just one hyperspace, but actually several terrifying layers of it. In the Black Ocean series by J.S. Morin, the setting's hyperspace, called astral space, had multiple layers, and the deeper you plunged, the faster you could travel, but also the more horrifyingly dangerous it became to navigate. Something remarkably similar applies in David Weber's classic military sci-fi series centered around Honor Harrington, with multiple levels. So civilian and commercial traffic in Black Ocean stuck to the shallower levels, military ships pushed into deeper lanes, while suicidally daring vessels dove even deeper still. Amusingly, in that series, the hand-waving explanation for hyperspace was literally magic, accomplished by wizards casting spells and enchanting drives. Another setting that played with the idea of multiple hyperspace levels was the Culture series by INM. Banks, which featured both an ultraspace and an infraspace, respectively above and below our normal plane of existence. In most of these settings, it is assumed that gravity warps space in a way that makes hyperspace jumps unpredictable or outright hazardous. Often, celestial objects act as deadly navigational hazards even while traveling through hyperspace, suggesting a natural overlap or interplay between the two realms. This shared concept not only adds stunning realism to these fictional universes, but also highlights the universal appeal of blending the known dangers of space with the eerie unknown of alternate dimensions. Now, one might call that unrealistic, but if you can enter one realm from the other, that implies some exploitation of natural phenomena that has been discovered and tamed, meaning these two places do interact with each other, at least on some fundamental level. It's worth noting that the term non-Euclidean space gets thrown around constantly in sci-fi topics like this, and since we're exploring the actual science behind these concepts, that term deserves a proper explanation because it gets wildly misused. Euclid is the Greek mathematician who gave us the 5 axioms of regular geometry, which are as follows. First, a straight line can be drawn between any 2 points. This postulate establishes the concept of a straight line and states there is a unique line connecting any 2 distinct points. Second, a straight line can be extended indefinitely in both directions. Lines aren't infinite in Euclidean geometry. They don't have endpoints unless explicitly defined as segments, or unless physical reality itself ends, like in a finite universe. Third, a circle can be drawn with any center and radius. Given a point as center and a distance as radius, a circle can always be constructed. This generally extends to higher dimensional equivalents, like a sphere or hypersphere. Fourth, all right angles are equal to one another. This postulate ensures that the constant of a 90-degree angle remains consistent across the entire geometry. And fifth, if a straight line crossing 2 other straight lines forms interior angles on the same side that sum to less than 2 right angles, the 2 lines, if extended indefinitely, will meet on that side. This is also known as the parallel postulate. It implies that if 2 lines never meet, the angles formed by a third line crossing them must sum to exactly 180 degrees. There are also 5 common notions from Euclid that are absolutely worth mentioning. Things equal to the same thing are equal to each other. For instance, 1 whole, 2 halves, and 3/3 all represent the exact same value. If equals are added to equals, the results are always equal. If equals are subtracted from equals, the remainders are always equal. Things that perfectly coincide are equal. And finally, the whole is always greater than any of its parts. As long as these axioms hold true, you're operating within the world of Euclidean geometry. But any geometry that violates even one of these axioms, especially the famous parallel postulate, plunges straight into the bizarre realm of non-Euclidean geometry. This can range from the surprisingly mundane to the breathtakingly abstract, and things get even wilder if we throw those 5 common notions into the mix and imagine a reality where basic math itself starts to shatter. But here's the thing, it's not always mind-bending. Consider a simple set of train tracks, 2 rails running perfectly parallel, yet they appear to merge in the distance due to perspective. On a flat 2-dimensional map, those lines would stay parallel forever. But if you folded that map at an angle, those 2 lines would suddenly cross. Now that's not exactly earth-shattering, but it perfectly illustrates how warping the space where geometry lives can completely break Euclidean rules. Another stunning case involves spherical geometry. On a sphere like Earth, 2 parallel lines drawn on a flat map might look like they stay equidistant forever. But on the actual curved surface of our planet, those lines form great circles, and great circles always eventually collide. You could theoretically lay train tracks around the entire globe that stay just a few feet apart, but they would gently curve along the sphere's surface rather than remaining perfectly straight. These deviations from Euclidean principles reveal how the very nature of space itself can rewrite the rules of geometry, and they become dramatically more profound under relativity, gravity, and the warping of space-time. It's no surprise that writers and creators love to invoke the term non-Euclidean, though it's almost always used in a vague or wildly dramatic sense. In works like H.P. Lovecraft's Cthulhu Mythos or Warhammer 40,000, the term conjures visions of chaotic, incomprehensible realms where familiar logic completely disintegrates. But in most real-world applications, non-Euclidean geometry simply means that 5th axiom, the one about parallel lines, doesn't hold. The shocking truth is that we encounter non-Euclidean geometry far more often than we ever realize, and it's nowhere near as alien as it sounds. For example, countless video games construct entire simulated universes built on absolutely bizarre geometries. Take the classic Dragon Quest games on older consoles or their tablet versions. In those games, the 2-dimensional map lets players sail east or west and emerge on the opposite side, which makes intuitive sense for a globe. But sailing north or south does the exact same thing, meaning you reappear halfway around the planet without ever passing through a pole. This kind of map wrapping, while conceptually strange, was an incredibly common feature of older games. Yet this is trivial compared to what's possible without even adding extra dimensions. In 3-dimensional games, designers routinely craft environments that players explore seamlessly, but that don't physically connect to each other at all. These disconnected spaces can be logically mapped through a hyperspace-like structure, enabling smooth, invisible transitions between entirely separate locations. This reveals how non-Euclidean principles can be applied with stunning creativity, both in storytelling and in practical simulations, without ever requiring a full descent into incomprehensible madness. One family member is currently obsessed with Star Wars, particularly the Clone Wars, which feature something called hyperspace lanes. These conveniently allow the galaxy far, far away to be displayed in a 2-dimensional manner. Hyperspace lanes are stable paths through hyperspace, free from black holes or other disruptive influences, which would otherwise make navigation incredibly hazardous. Black holes and singularities are serious concerns for hyperspace topologies, since topology becomes wildly unpredictable around singularities, as well as cuts, corners, and other abrupt changes. Some of these hyperspace lanes are long-lasting and heavily traveled, earning iconic names like the Corellian Run or the Hydian Way. These routes are patrolled and form the very backbone of intergalactic civilization. However, most lanes are much shorter, requiring ships to periodically drop back into real space to check their position and recalculate their path. This limitation confines travel primarily to within the galaxy, which is a deliberate plot device designed to minimize intergalactic activity. The Yuuzhan Vong, one of the few exceptions, are no longer considered part of the official canon, though they remain a fascinating story arc. What's truly remarkable is that hyperspace in Star Wars seems to be significantly affected by gravitational phenomena, making the deep core of the galaxy incredibly dangerous and nearly impossible to navigate. This region, like the centers of most spiral galaxies, is packed with black holes and other extreme space-time phenomena. While the supermassive black hole at the center of the galaxy is notable, it's not unique or essentially important to hyperspace navigation. The depiction of hyperspace in Star Wars is absolutely iconic, with ships traveling through an artificial pocket of real space while stars flash by as brilliant streaks of light. This real space pocket conveniently avoids the complications of strange physics aboard ships during transit. It's akin to the earlier concept of a congruent universe with different rules, enabling dramatically faster travel. The idea that the real universe influences your path through hyperspace makes perfect logical sense. Navigational challenges, such as needing to drop out of hyperspace to check position and recalibrate, reflect the inherent unpredictability of long-distance travel across tens of thousands of light years, where because of the speed of light, those stars you see are not where you actually think you see them anymore. Even minor gravitational variables and cosmic phenomena can disrupt a predicted course, requiring frequent adjustments for safe and efficient travel. Now, you might wonder what entering hyperspace actually looks like, and the honest answer is, nobody truly knows. Without understanding its properties, it's impossible to describe with certainty, but odds are it would not be the iconic Star Wars Starstreak look. In Star Wars, it's depicted as entering a pseudo-acceleration stage, where the stars blur with speed as you zip off into the distance until you wind up in a blue tunnel effect, which you can only do away from a planet's gravity, but there's no real basis for that. You could enter a higher dimensional plane at any speed, from any elevation, even in a degree of warped space-time, so there's absolutely no need to exit that planet's gravity well either. You are, depending on your model, sliding at a right angle to reality and into somewhere else entirely. It's a little like asking where on a building's floor plan you can put a staircase. Fundamentally, anywhere, as long as it doesn't conflict with something else you need, like a room or plumbing. But if you ask whether a staircase is on the first floor or the second, the answer is both. And someone looking at a staircase on the first floor versus the second floor would see two wildly different looking objects. A flat map of each floor showing the staircase won't show the same thing, because it's a two-dimensional image of a three-dimensional object that essentially punches through two or more flat spaces, the various floors or stories of a building. And this isn't the classic portal look of a two-dimensional window, at least not on our side. If you enter a two-dimensional space, you might see a flat window, and similarly, moving from a higher dimension into ours might appear as a three-dimensional window inside a four-dimensional or higher space. Going into a four-dimensional space would probably look like a sphere to us, though a tesseract or something similar might be the case. And that would likely involve a bizarre quasi-kaleidoscope effect as you move toward it. Folding space, on the other hand, ought to look like a straight-up blend of the initial view with the incoming view. So a doubling up of stars, two completely different planets sitting next to each other, and so on. If you're jumping into another universe with different properties, you might get this blend, but you also might face the terrifying problem of there being no photon or photon analog in that place for you to see and detect your way around. Nothing but absolute darkness, even darker than the normal boring emptiness of space itself. Now, if we're talking a congruent universe style of hyperspace, then entering or exiting might look like a violent distortion of space-time, similar to an Alcubierre drive. It might also look a lot like two-way wormholes or Stargate-style portals. The reason for the similarity is that in either case, you're still leaving the local piece of the brain and breaking causality with the outside observer. A warp drive and a hyperdrive both have a certain event horizon-like effect in that regard. Alternatively, if we're talking a four-dimensional style of hyperspace, then a strange sort of classical effect may happen to you. There's a famous illustration involving flatland and how a ball or an apple would look passing through it. All the two-dimensional people of flatland might observe is an object growing larger than smaller as the three-dimensional ball passes through their flat paper world. Likewise, as you are plucked from this dimension and elevated somewhere else, we may witness some genuinely horrific effects as parts of your body and your ship are sucked into another realm before other parts follow. But if we're talking hyperspace, as in the bulk from earlier, how does that actually work? How do you have a wormhole to nowhere? Well, you might not. Not at all. For that scenario, you might have to bring a bubble of stable space-time with you, a basement universe according to some theorists, so you never actually see hyperspace beyond the bubble. All an outside observer would see is you and your departing ship being pinched off from this part of reality, which may look like entering a short-lived wormhole to a basement universe before the wormhole snaps shut behind you. This would be a truly staggering feat of impossibly advanced engineering. Now, to close things out, let's break down the differences between warp, hyperspace, and wormholes, another incredibly common sci-fi method of faster-than-light travel. Warp drive, like the kind depicted in Star Trek, operates on subspace, which is a real mathematical concept, though its portrayal in that franchise is a bit loose and inconsistent. They generate a subspace bubble around them, which also has a real space pocket the ship itself is in. Space compresses in front of them and re-expands behind, meaning they cover less space rather than breaking light speed. The Alcubierre warp drive uses that approach via negative matter, and there's a whole fascinating rabbit hole to explore on that topic alone. Hyperspace and wormholes are two wildly popular concepts in science fiction that offer tantalizing ways to cheat the brutal constraints of interstellar travel, but they represent fundamentally different approaches, though both are pretty broad terms in both science and sci-fi. Wormhole usually refers to an Einstein-Rosen bridge specifically. Hyperspace is often envisioned as an alternate or higher dimensional space that connects distant points in our universe. Travelers jump into this strange realm where distances are compressed or physics allows for faster movement, enabling them to bypass the speed of light entirely. In contrast, wormholes are theoretical shortcuts through space-time itself, forming tunnels between two distant locations. While both ideas stretch the imagination and space-time itself, their underlying principles and mechanisms diverge significantly. Hyperspace draws inspiration from higher dimensional spaces theorized in physics, like those explored in string theory. The experience of hyperspace is often portrayed as disorienting, with unique rules and bizarre phenomena. In fiction, it's also a solution to the daunting vastness of space, allowing faster-than-light journeys without violating special relativity outright. Wormholes, on the other hand, are more firmly rooted in theoretical physics, at least the ones originating from Einstein's equations of general relativity, though there are other fascinating versions worth examining. Einstein-Rosen bridges represent a possible way to connect 2 points in spacetime by bending or folding the fabric of the universe, usually by use of negative matter, which theoretically bends spacetime the opposite of how normal matter does. Normal matter compresses space and slows time, while negative matter presumably expands space and maybe even speeds up time. While mathematically plausible, traversable wormholes face staggering challenges, including the need for exotic matter with negative energy density to stabilize them. In stories like Stargate or Interstellar, wormholes offer a direct path from one place to another, often depicted as instantaneous travel through a tunnel-like structure. But here's the shocking truth. They would not be instantaneous at all. You would have a real and lengthy journey time into a wormhole and through its throat, and then out the other side, not just a few fleeting moments. Both concepts come with inherent dangers and terrifying limitations. Hyperspace travelers might face navigational hazards such as becoming hopelessly lost or encountering native entities, as seen in Babylon 5. It also requires advanced technology or special skills to access and navigate. Wormholes, while potentially more grounded in physics, present their own jaw-dropping challenges. They may be unstable, collapse under their own gravity, or lead to completely unpredictable destinations. Their extreme energy requirements and dependence on exotic matter place them squarely in the realm of speculation too, so don't assume they are more real than hyperspace. In fact, the odds might actually be better on finding a way to pass into other universes and discovering some congruence in them than ever finding negative matter. But for now, both remain trapped in the world of fiction and deeply theoretical papers, with absolutely no pathway to experimental proof, let alone practical application. Hyperspace, with all its mysteries and lurking dangers, captures humanity's burning desire to shatter every boundary and plunge into the unknown. Whether it serves as a gateway for crossing mind-boggling galactic distances or stands as a powerful metaphor for venturing into realms beyond all comprehension, it reminds us of the truly limitless potential of human curiosity. For now, it lives firmly in the realm of fiction, but history has proven time and again that today's wildest imagination often becomes tomorrow's groundbreaking innovation. Perhaps one day, we will actually step into hyperspace for real, embarking on journeys that completely redefine our place in the cosmos. Until then, it remains a tantalizing dream, waiting for that single spark of discovery to transform it into breathtaking reality.